to introduce Maurizio Paolillo, who have been collaborating for quite a few years now. Maurizio is a professor of physics at the University of Napoli, physics department. He's an expert on variability, but also quasar surveys. He's also heavily involved with LSST. So if anybody is interested about it, I don't know if you are going to talk.
Yes, I'm not sure.
So you will talk about it. Right. So Maurizio got his PhD from Palermo University in Sicily. During his PhD years, he spent half the time there and half the time at CFA, working with Pepe Fabiano, as we were telling you today. And then he moved back to Napoli for a year as a postdoc, and then moved back again to the Space Telescope Science Institute, working with Giacomo. Right? Yeah. He's been there for 2 years, and then came back to Napoli, where he has been since. So I will now ask Maurizio to start his talk.
Thank you. Yes, it's always a pleasure to give talks here. I'm a frequent visitor and I enjoy it a lot. It's very productive and very nice environment. So my idea today was to tell you a lot of things, too many actually, about variability, ranging a little bit from X-ray to optical, and with the idea of showing what we expect to do in the near future and why it's an exciting time to look on to use variability to study supermassive black holes. So in general, this is the typical image of an AGN. Let's see. Oops, it's stuck. Let's see. It was working perfectly a second ago. Okay, so this is the very complicated scheme that we have of what we believe is a phenomenon that we call AGN. Supermassive black hole accreting from an accretion risk with some external region obscuring the central part, with an X-ray corona that we don't know exactly where it's located, how extended it is, what physically produced it, if it's here, if it's on top of the disk. And the radiation produced in this complicated structure is emitted at every wavelength because of the different temperature and status of the plasma in all these geometrically complex structure. But what I want to remind you is that so far we have knowledge of all of this directly only for 2 objects in the universe, which are these 2 here. This is the only 2 supermassive black holes, actually the only 2 black holes that we ever image directly, more or less. And so everything we know and the entire scenario that is depicted by this toy model that is shown here, most of it comes from timing studies. Of course, there are also spectral studies, polarimetry studies, but timing has a lot to do with it because, of course, if you look at what are the time scales, you see that here, depending on which region is emitting, the central part in X-ray, the UV optical, the brown light region, the torus, then the distance in terms of gravitational radii is different. And so the light crossing time is different. And so you expect this object to react to changes in the center on time scale that go from hundreds of seconds to hours, depending on the mass of the black hole. And then it scales with the wavelength. As we move outward, the time increases, the temperature decreases, the time increases, and so we can sort of map the structure of this object looking at how the changes propagate to this structure. The point is that we don't really know what causes the changes, and we don't really know exactly how they propagate, inward, outward, and so on. It's complicated. Now, all this complexity is usually reflected very well in the spectral energy distribution. This is a sketch of the complicated spectrum of an AGN, in which you see all the components arising. So you have different spectral components from the X-ray corona, from the torus, from the disk, and not all of them are well known. They change from object to object. And then if you have more radio loud object, it's even different than this one, because you have these lines here in which the synchrotron emission dominates above everything else, and so you don't see many of these components. So this spectral complexity is reflecting the geometrical complexity, and we have an idea that these objects are fairly similar across the universe, because if we look properties like, for instance, here the alpha X, the ratio between the emission in X-ray and optical, more or less with some scatter, with some variability, they're constant up to high redshift. So, and this is an index of how much power is reprocessed from the X-ray to the disk. If we look at, for instance, the slope of the X-ray part, which is reflects the condition in X-ray corona, so the innermost part around the AGN, also this is more or less constant. So we believe that all AGN, the basic structure of this AGN is the same. Now, when you do this type of studies, the complicated factor is that you can do spectroscopy and you see beautifully, for instance, in SDSS spectra, the lines that shift in wavelength as you move in redshift, and you can see that you always find more or less the same lines. And in fact, if you superimpose high redshift spectrum on local ones, more or less you see the same things, except the absorption of the Lyman rate because of the intervening hydrogen. But you see the same lines, more or less same abundance of metals and species and so on. And even the iron line equivalent width is the same. Now, it would be interesting to know, but then are also timing properties the same? But timing properties are always very complicated to show. You cannot make an easy figure like that. And so I have to convince you that we can actually trace the properties of the black hole across the universe at high redshift and say that they are more or less the same. So the way in which we usually study variability, if you have a nice light curve like this, you can use the power spectrum, which is basically the Fourier transform of your light curve, which is telling you how much power you have on each frequency, on each time scales. And if you have a very good light curve, you can usually construct a power spectrum. And what we know today is that probably many AGN, the nearby one in which we have very good monitoring, the power spectrum is a power law, but with a bending or a break. It's not totally clear. And the presence of breaks is very interesting because it means that there are some typical time scales in these objects, which have to relate with the physical properties of the black hole or of the accretion flow. So far we usually detect, especially in X-rays, which is the innermost part of the accretion flow, the high frequency break here. In one object so far we've seen a second break here. We expect this to go flat because otherwise the power would diverge when you go to low frequency. But this you can do only for a bunch of local AGN with masses that are not as large as quasar masses, and many of them are peculiar or partially obscured objects. So if you want to know if all the objects in the universe behave the same way, you need possibly dedicated long campaign, or in the last decade or so, we've been using more and more large survey data because they're starting to probe not just the deep universe, but also the time domain, because the time coverage is increasing. And the reason we believe there should be a link with the physics is because very simply and naively, whatever time scale you take, the dynamical time scale, thermal time scale of the disk of the accretion flow, all of these are believed to scale somehow, at least with the mass of the black hole, so the region becomes larger and the scale should scale according to the mass or somehow the mass, and possibly also with the height of the disk, which then may be related with the accretion rate. So the fundamental parameter of the accretion, which is regulated by the mass of the black hole and the accretion rate, possibly the spin, but that's still very debated, are should be hidden into the variability that we observe. So what did we observe? In the local universe, we observed so far spectra like this. These are a bit old now, but the plot shows basically makes the point. If you take a sum of the local AGN with different masses, you can clearly see that the power spectrum has a break. I point out that this is not as steep as the previous one, because here we're not plotting power, but power multiplied by frequency. So this part here is the one that it was a slope of about -1 before. So it's flattened out. So this is the high frequency break. And you can see that it shifts up as the mass of the black hole decreases, which you expect, because it means that when a black hole becomes smaller, you have more variability on shorter time scale, because you have a smaller region around the black hole that it's capable of varying. When it becomes large, the variability is mirrored out over a larger region. And in fact, there have been claims that a relation of this type of the break here with the mass of the black hole to some power and the bolometric luminosity of the object to some power, which probably relates to the accretion rate, holds across not only orders of magnitude of the AGNs, but all the way down to galactic sources. This is the famous galactic black hole. So the variability would just be probing the intrinsic physics around black hole, and that they all scale the same across several orders of magnitude. Yes.
This break is the second break that we saw in the first. This one. Okay.
This one is not visible. Okay. It should be down here somewhere, probably.
And this break is related with which time scale?
This one?
Yes.
That's what we don't know. Okay. It could be, you expect some, for instance, if you truncate at the innermost radius of the disk, of course you expect that variability falls. But this is the corona. And so where is exactly the corona located around the black hole? We don't know. It's a middle part of the disk. It's the base of a jet. So, and I think the results are not conclusive. There are different models that can explain part of it, and none of it, explains fully the time scale that you want in all cases. So it's still very empirical. We don't have a model to exactly show what's happening. But what I want to convince you of, that even though we don't really know exactly what's going on and the physical mechanism in detail, but this relation, we can use this relation, we can check if they hold across the universe, and in particular if the variability is more or less the same everywhere. So if you want to push further back, then you don't have long dedicated campaign, and to see the faintest AGN, you have to use surveys. So I show you an early work by Almai et al. In 2000, in which they use ROSAT data from the Old Sky survey. And I like to show this to show you what are this is sorry, it's a bit small. It's the variance of the light curve as a function of luminosity. So it was discovered very early that there is an anti-correlation with luminosity, which is the same that I showed you here, right? And what they were showing is that this holds also for higher redshift AGN, but these are the actual individual point measurement of the variability for these sources, which are enormous because there are few photons for every source. So the statistical uncertainty are large, but second, variability is intrinsically stochastic. So if you repeat the observation for the same object, you will not get the same point. You need to average multiple observations or similar objects. But nevertheless, if you average this mass, you get a trend like that, and it's statistically significant. So this is one of the earliest attempts to show that this anti-correlation holds also for higher redshift black holes. And then the next attempt, I think, one of the next, was trying to do it with the Chandra Deep Field South, which is the deepest X-ray observation in the universe. This was the image of the first megasecond in 2002. Now I'll show you we went all the way up to 7 megaseconds. Now Chandra is dying, so unfortunately we cannot do this study. more, but at the time we try to reproduce something like this, and this is the scatter plot that you get. You still see an anti-correlation. You could wonder if all the AGN work the same, because the high luminosity ones are higher than the rest. And this is actually a selection effect, but it took a long time to understand really what it was. But the anti-correlation holds. So it's telling you, as the black hole becomes larger, it's usually more luminous, you have more energy release, the well is deeper. And so, but as become larger, also the variability should decrease because the size of the emitting region is larger. And so this is sort of expected from what I showed you before. So a similar work done here by Yosif, for instance, was showing that in fact, you can plot the luminosity and the variance of this black hole, and assuming that the break and the scales in this way with this empirical relation, which is the one that I showed you before, the famous line that connects galactic to extragalactic black hole, more or less, you can predict what the power spectrum, what the variability should be. And even here, there was a suggestion that maybe at high redshift they could be more variable, which now we think we don't believe anymore. But the problem is the huge scatter in the data points. But you can see that this anti-correlation now with luminosity is not really linear. It falls at some point because you get to the point where you don't observe any more variability. Simply the black hole is too big. It's very luminous, but it is also very large, and so the variability drops completely. And that's what you expect. Similar work were done with another service like Cosmos, the famous Cosmos field. This is, in my opinion, is interesting because in Cosmos field, this is the sampling of the Cosmos field, very sparse. But when you look how many times every AGN was observed, the number of detection peaks at 3, 4. So they try to do variability with 3 points per light year. So in the beginning, I remember I thought it was useless. And then we realized that actually you can do a pretty good job if you have enough objects together and you assume, of course, that they share some property. In fact, they showed again that the variability anti-correlates, in this case, with the black hole mass directly, because they didn't have luminosity, they had black hole mass measurement from spectra, so you can directly put in the black hole mass instead of the luminosity, which is a proxy, but also depends on the accretion rate. But they were not seeing any dependence on the accretion rate, for instance. So what I think we've done so far in this field, we put together the 7 megasecond taken from 1999 up to 2017 in the Chandra Deep Field Sat. This is an animation of the stacking individual exposure that we're taking almost over almost 20 years. And this is a zoom in that I use with my students to show them what Poisson statistics is and what the signal to noise means. And you can clearly see that the points, the sources appearing as we stack more and more observing time. And actually, Chandra had such a low background that you could even push further, but it would require an enormous amount of time. But we're not background limited yet. You could even do better if you had another 20 years of observations. And so this is, the deepest observation that we have in X-ray of the universe, and all of these are AGNs. The fact that you compose this assembling several epochs means that you can make a movie with it. And so this is the movie version, the differential version. So if you look at every epoch, you will get light curves like these ones. And now you have, pretty, I wouldn't say good, but decent light curves. There are huge gaps. You will see the green bar that jumps, but you clearly see that the AGN switch on and off, and that's a sign that these are point-like sources, relatively small inside galaxies. So the point is that to go from these data to the power spectrum that I showed you before is not trivial. So this was the light curve that I showed. And if this is your power spectrum, in reality, when you have light curve like this, it's very difficult to get the power spectrum. You need repeated measurement. So, but you can compute the variance. And the variance is the integral of the power spectrum. So if you assume a law like this, which is this one, and then you take an integral between the minimum and maximum frequency, you get the variance. So you can use something that is like a variance frequency plot instead of directly the power spectrum. And you see that when this bends, also this one bends, and there is a break. And so you can use this to trace the properties. And then you can take advantage to the fact that you can sample different frequency with your data, because for instance, if you take this part, you sample a range of frequency, this part a range of frequency, and so on, and you can go down. And then once you put this all together, we decided to put this together, but then merge it with low redshift sample, so that we could try to trace the variability all the way up to high redshift. So the sample is a sample that includes, for instance, ASCA source, XMM, RXT, Swift, and for the high redshift, these two samples here, the Chandra diffuse south and the Cosmos that I showed you before. And so that we go from basically 0 to at least redshift 3. And the complicated thing here is that we have different data from different satellites, sample on different time scales with different statistical properties, different masses. So this made the analysis quite complicated, so it took us some time. But the idea is that to account for that, for each one of these data sets, you have to see what your model would predict, what you expect. So you compare the data point. These are the data points that Chandra diffuse south. They're horrible, of course. They jump everywhere. But the average of this point is more or less correct. The model is this red curve here, and then we were just approximating with a line. This is what the Cosmos tells you, and this is the model. But then you see that when you get better light curves, sample much better on shorter times, like this ASCA, you can see how well the model follows the point. So the problem here is just that these points are very scattered because intrinsically they're very low statistics and very sparsely sampled. So it's normal, but the average still contains information about the variability. So you put these together, you add these other two samples here. This is the one on the very longest time scale. In this case, the time scale is so long that you don't expect any change in variability with black hole mass, because you are way below the break. So if nothing, according to the model, it doesn't change anymore with the black hole mass, and in fact, it's pretty much constant. And then when you put everything together, yes.
Can you give again what the different lines are?
Okay, yes. So the black points are the data, the variances that we measure for each source. Then the dotted line is the model that we're trying to fit. This is one of
the broken one.
Yeah, exactly. But as a variance, not as a power law. So this is the integral. The red points then is the expected value that you expect at the mass of each. And then to make things simpler, we just approximated with a line. So we compare the average of the red point with the average of the black, which are the two lines, just because adding more complexity doesn't add much and complicates the picture a lot. So we're basically trying to say, okay, once we account for the mass of each object, which gives you different variability amplitude, can we derive, the average for each sample and check if the model is able to predict the average that you expect at this average black hole mass, at every redshift, every luminosity, and so on.
So the squares are the value of the model
at the black hole mass. Exactly. So you have to compare each black point with each red point.
Yes.
Now, here there are no error bars, but the reason there are no error bars because the individual statistical error bars are useless. That's not the real scatter here. Here, the real scatter is produced by the variability, but not by shot noise. Is the variability. So if you measure this next year, this point will be here, and it's perfectly normal. It's part of the stochasticity. So what you want is that the average of these points is where the model you expected the model to be. The average should be there. Yeah.
This variability should be reflected on the stress variance.
Sorry?
But the variability that you say that if you measure next year,
Yeah.
will be different. Shouldn't this be reflected on the excess variance?
Yeah, you will have a different excess variance.
So
You expect that this point fluctuates maybe around here
sigma squared should be higher.
or smaller. It's random. So every time you measure it, it has a different value. On average, is your temporal average, but the instantaneous measurement is follows.
Yeah, what I mean is that you consider this as the mean, but it's not actually the mean.
No, the mean. I'm saying that the mean is the mean of every point here with respect to what it would do. Right. So each one of these points should fluctuate around this mean value, which is.
So you are using the other data points in order to estimate what will be the mean.
We're estimating the distance of each point from the model here, and your assumption is that each one of these points is distributed in a Gaussian way around the mean, which is true on long term. So you don't have multiple points for this mass. Okay, but you have points at every mass, and each one of these should scatter around the mean.
So you fit your data with the model, and the best fit value at each mass is what you assume to be the mean.
Yes, and you have to have this simultaneously for all AGN, all data set and all redshift, all luminosity simultaneously.
Straight lines.
It's because instead of comparing every single point, we recur to a linear approximation.
That's it.
Because here you can fit it here, but go here. What is it?
Yes.
It makes no difference at all.
But you perform a global fit for all the data points.
Yes.
Okay, so effectively you are using the whole assembly of the data.
Yes.
What is the mean?
Yes.
Okay, fine.
Yes, you're using, but you have to account that each one of these has a different range of masses.
Yeah.
There is also another point that I didn't show. Each one of these data set has different time scale of sampling. And now, because each object is a different redshift, they're sampling a different part of the power spectrum. So for each one, you have to integrate the proper part of the pattern. That's why you see the model, but then the red point oscillate, because actually for each source, you have to compute what you would expect at that redshift integrating that power spectrum for that mass. So it's a bit complicated. That's the only way to account for all the properties of the sample, right? So luckily, when you do that, this is a result. The black points are the fits, they are the data set. So is the frequency that we sample, the maximum frequency of each light curve for each sample. And here there is the variance. And the red points is what your model would predict for that sample, right? And as I told you, we cannot put just one curve, because for each data set, you have a slightly different model, because it depends on the range of masses and time scales. So this line here is just to show you the average model, but in fact, you have to compare each point with the red symbol. The fit is done between the black and the red points, because they will scatter around the average model, because this one maybe samples a little bit longer light curve, another one a little bit shorter. So in one, the variance is expected to be higher, and one is expected to be lower. But when you do that, what we found, and that you can reproduce both the amplitude of this variability and the slope of this relation pretty well, and they're reproduced by one single model, provided that this model allows for dependence on the black hole mass. So this now is telling us that if you take all AGN from time scale from days to years, redshift from 0 to 3, and mass goes 10 to the 6 up to 10 to the 9, you can move on the average properties, not of every individual, but the average property of this population are well reproduced by the same variability model. And so the physics should be the same. There will be individual differences, but across the universe, even the timing properties are the same, which is a reflection of the physics and the structure of the object.
So
Yes.
maybe you already said that the model is the same for each data set. You are simultaneously fitting
Yes.
every data set with the
The
same.
model is this.
Yes.
Is this power spectrum where you have the break depends on the black hole mass, and here you could put a dependence on the accretion rate. So you're taking a very simple model. There's just a dependence on this break on the mass, and there is space also for a dependence on the accretion rate. It's hard to probe in this case, but you're saying, can this describe more or less the average variability of all AGN across units? Yes. On average, yes. The individual one will maybe do weird things, but on average, yes.
But they're using the same model for each data set.
The same model, I mean the form, because
Yes.
then you have to put the proper mass for each object and time scale for each object. You have parameters here. You have the black hole mass.
Yes.
You have the minimum and maximum time scale which you're integrating. So if you want to compare with the real data, you have to take into account for every single object, what is this, what is this, and what is this. Okay. Then you do make a prediction, and then you constrain basically this S here, so the slope of this relation here. And you see, can we model everything with this type of power law? Well, bending power law. In fact, the result is yes, that you can. In reality, we found, for instance, that this part is steeper than was predicted in the past. The power spectrum drops more steeply, but more or less it's fine. Now, what can you do with that apart? The most variability is interesting for across the universe. Is that this is a work done with Antonis Georgakakis, that because if the variability depends on the black hole mass, variability becomes a new observable that you can use to constrain other relations. For instance, imagine you take a galaxy sample in which you have a stellar mass function, so you take a galaxy sample, and then in each one of these, we know from statistical studies what is the accretion rate distribution of AGN in this galaxy. So you can populate this galaxy with AGN, accreting matter. And now we know that there are some scaling relation between the stellar mass of the galaxy and the mass of the black hole, which we don't yet fully understand. So we're trying to understand how the mass of the galaxy relates to the mass of the black hole. So if you want to decide which model of the scaling relation is better, now you can, in addition of observing the luminosity distribution of AGN or the mass distribution, now you can, and the statistics, you can also use variability because that's related to the mass. So what you do, you also assign to each object here a certain amount of variability according to the model that I just described. And then you get a variability prediction, and then you compare with the data. So for instance, in this case, it was able to show that you can predict what you see in the chamber that it's out a little bit better with one scaling relation model with respect to another. So this is interesting because you now have a new observational quantity that can be folded into your cosmological studies to because it's in indirect measurement of the mass of the black hole. And or the other thing is, for instance, variability comes into account in these type of studies when you have quasars. This is the Hubble diagram of quasars, in which with the result and Medalus claim that there is a tension with the standard model. So they built the distance, the Hubble diagram using sample of a very well constrained sample of quasars. And if there is tension with the standard model, most of the scatter, and so the uncertainties that you have in the final parameters, and how well can you say that there is a tension, depends on variability. Because a large part of this scatter is due to variability, because the luminosity of this object changes. So if you can constrain very well the variability of this object, you can account for how much of this scatter is due to variability and how much is really the uncertainty that you have intrinsically on the cosmological path. And now I see that all of this is going toward the future mission like eROSITA or that has now been taking 5 epochs, I think, of data unfortunately was stopped due to the war with Ukraine. So, but this is sampling the whole sky, and especially around the polar region, there are hundreds of observations. So you can have pretty good light curves, although most of the sky, it's 4 or 5 data points. And the future missions like EXTP, which is an Italian-Chinese mission, StarX, which is a proposed American mission, you can do much better than what we did so far, because as you've seen, our sample are very heterogeneous. We don't have an homogeneous sample across the universe. Now, I'm running horribly late, so let me say something about optical variability. The optical variability, of course, instead looks at the disk. So in the optical, we typically, sorry, the time scale are larger because we're looking at an outer region, and we go from days to years in variability. That's what we expect, and we're tracing the structure of the disk. Now, in optical, very often we instead of doing the power spectra, most of the literature uses the structure function, which is sort of the same tool, but instead of the frequency domain in the time domain. So you have time here instead of frequencies. And there are advantages and disadvantages for doing both. This probably is the proper way to do it. This one is much simpler to divide, but the two are linked together. If you have one that is this slope, you will get this slope in the structure function. So the structure function is basically the average magnitude difference between two epochs. So it's related to the variance of the light curve. And to study this on large sample, this has been done already in the past, but there is no clear consensus about what the model is even here. One proposal is this damped random walk, which is damped random oscillator, which works over some time scale, but not everywhere. These, I think, are Vincenzo's simulations, right? And plus, if you look at the literature, there is no consensus if the variability clearly scales with mass, accretion rate, bolometric luminosities. Sometimes yes, no, mildly, strongly. So each work uses a different model. Some fit the light curve, some fit the power spectra, some fit the structure function. So people are still trying to understand what's really going on. And there are works like this with Kepler light curve that show that the slope of this power spectra, for instance, is -3, which is what we saw in the X-rays, but it's not what this predicts. This predicts -2. So the model are probably not correct. So in this case, also you can use large samples. So I'm showing you an example of work that Vincenzo here is doing with me and Yosif, which is taking light curve from the stripe 82 of SDSS. You have almost 10,000 quasars, and you have 60 visits in this light curve. They're almost simultaneous in different lengths. So you can assemble a very good sample that spans a large range in black hole masses, bolometric luminosity, and redshift. Unfortunately, because these are ground-based experiments every 6 months, you have these points here, and you have basically 3 epochs. If you don't consider every single observation, which has a lot of statistical uncertainty, you can average. And so you get a power spectra, which is done on 3 points again. But you have a lot of sources, so you can put them together. And Vincenzo is finding that, in fact, when you look at this power spectra, there is a clear trend with the black hole mass in the amplitude of this power spectra, something reminiscent of what we find in the X-ray. And there is a trend with the accretion rate as well. In fact, these seem pretty independent. In fact, you can model them with a plane, two-dimensional plane, and you can show that the points lie very well on the three-dimensional plane, both in amplitude, and this is the slope of the relations. They both are modeled by a plane. And so now to see the full power spectrum, yes, okay. You don't, using just SDSS alone is a bit restrictive because you have only a number of years of observation which the survey was taken. What we're trying to do now, not just us, but many people, is to put together different surveys simultaneously. So again, this is what Vincenzo is trying to put together the points from the SDSS, including the one from Pan-STAR and the ZTF surveys, all surveys that have been ongoing, that are still ongoing, some of these. And you see that they probe different timescales. And when you put them all together, you can probably start seeing emerging the full power spectrum of this object with an indication that there is possibly a break here. This is not a conclusive result, but you cannot fit everything with just one straight line like Dunn-Farmer work suggests. And if what he found for SDSS is true, that it changes with the amplitude changes with mass, you should have something like that. I think it's a preliminary plot that we were playing around, but you should have a different amplitude in SDSS. In this part, it's more complicated because on short time scale, it's very different on fast variability to see the amplitude difference. So now you have a picture which is emerging that is telling you that probably we can reconstruct also in the optical the properties of this sector. And we're trying to add also these points here that are from Gaia, the keys. And to have, very well sample light curve about this. Now, where all this takes us? Because we want to use variability both to study the physics and to try to detect AGN. And this is especially important for the near future that is going to come. In particular, because of this machine here, which is the Vera Rubin telescope that will come very soon. So together with all the methods that we use to detect AGN, through spectroscopy, XCD, creating supermassive black hole, variability is ubiquitous. All AGN are believed to vary, more or less. And we want to see how we can monitor them. So this has been done in the past. It's nothing new. AGN quasar were discovered through variability. So this is an example of node work in which the points here, the field points are the variable source, and 60% were confirmed AGN. So you look at the variable sources, and you see that 60% are actually AGN. Or other work that have been done, for instance, with Hubble Space Telescope, looking at the difference between two epochs. All the objects scattering more than a certain amount are possible AGN, and in fact, they're mostly confirmed. But then you have some surprise. For instance, in this case, only 10% are detected in X-ray. So it seems that you're looking at faint AGN, and in X-rays you couldn't discover. But you discovered through optical variability. So a few years back, we started doing this type of work in supernova surveys, because most of this type of study come from surveys that are designed to find supernova to the cosmology, but then you can use them, the time domain, to do everything else. With the VST telescope, which is the 2.5 telescope in Chile, the Italian telescope. And it's because there were surveys on some of the most famous fields, the Cosmos field, the Chandra Deep Field South, LISS1. And they started imaging these areas here. And incidentally, these are also some of the ones that LSST will look at. And the nice thing is that when you do this carefully with a dedicated survey, this is one of the results, for instance. These are the RMS of the light curve, so the variance or the standard deviation. And the triangles are the X-ray detected sources. So after 6 months, we could detect this number of X-ray sources with variability. When we waited 3 years, then the number became like that. So after 3 years, all of these are detected. So we showed that you can reach 40–50% completeness just through optical variability, while usually X-rays is the most complete way to find AGN because it's more penetrating and you see through obscuration and dust. And now the point is, can we do better on longer time scale? These objects have properties that show in this diagnostic diagram that they're actually, most of them are AGN. This is the AGN sequence, for instance. All these points are variable objects, and most of them are confirmed to be AGN. So let me show what you do when you extend the time scale. First, let me show that some puzzling results, for instance, are this. This is the structure function. So these are how much they vary as a function of time, as you expect when you wait longer and longer time scale, because we have this red noise spectrum, they vary more and more. So non-variable sources are here, AGN vary more and more. But then when you look type 1 and type 2 AGN, so the unobscured and obscured, the type 2 are almost flat. So the question is, are they the same object, or is this telling us that the unified model in which AGN are different manifestation of the same thing, just oriented differently is different? Is this because just some of the light is reprocessed and the variability is diluted, or not? Otherwise, this should be just a downscale version of this, just painted, but with the same variability. And this is not clear there, because there are very few samples properly studied in variability. But because the variability is a structure, we want to know if it tells you that the structure of the object is the same or not.
Sorry.
Yes.
So that the plot on the left is dominated by the type 1.
Yes, exactly. This I think was the whole sample, because this is a minor fraction. So when you put everything together, you basically dominate by type 1. When you then divide the pure type 1 sample and the type 2, the type 2 basically flatten out. You can see from the arrow. So there is some variability still here, but it's less than 30% of the type 2 on the longer term.
Type 2 varies less,
Yes. And now we try to do this. Now we have 10 years of observation, because we continue to do the campaign in Cosmos. And this is what we get now going to 10 years. So we got all that, and then it seems to flatten out, which is a bit surprising to us. We have not understood yet. This is a very preliminary result. It's clear, because if it was going exactly like that, now this would be consistent with the damped random walk that I was telling you before that doesn't work. This would work with that model. So we have to understand if this is correct. And the other thing is that because it flattens, it means you will not find more AGN if you look longer, which is a bit disappointing, because we were really expecting that with 10 years we will get almost every AGN variable, but we don't. So for this reason, we're doing all this work because, as I told you, probably in 2025, the new facility, this 8-meter telescope with 10-degree field of view, will enter into operation. This is an American facility, but it's part of an international collaboration to observe the sky for a 10-year period every night. So this is a movie of how the observation will go. So every night it will observe for 30 seconds every patch of the sky, and then move to the next one and do that continuously. So most of the sky will be covered every 3-4 nights. And this will be done in UGRI, ZY bands. And so you will basically have a movie of the sky for the next 10 years in the optical, which is unprecedented. In some areas will be covered much more frequently. In fact, in the end, you will have this map. Some fields, like the deep drilling fields, will be covered every night or every 2 nights. And so you have fantastic light curve for 10 years. And then variability becomes one of the main factors to detect objects. So I'm almost done. Let me just show you that we're doing a number of studies to see how to extract AGN in these samples, both to traditional method, cross-correlation of bands, but also for those of you that are interested with machine learning attempts. A lot of machine learning methods that we tried, and they all reach very good completeness and purity through variability and photometry. This is a fun one, which is actually not even variability. We feed images to a neural network with objects in which we know there is an AGN from X-rays or spectroscopy, and we ask them to find all the neighbors to this object. And he identifies these objects here, and 60% of them are AGN. And this is just giving a snapshot of the object without any other physical information. So it's very interesting, challenge, promising that you can do so much with such a simple to do. And the last thing is that now we are continuing to monitor these fields with the VST, which is the much smaller version of this. We're now taking the center of these 4 deep drilling fields. I would just want to show you that we already have more than 1,400 single exposure since 2011. So there is a huge effort to reduce this data. Unfortunately, the sampling is very sparse. Some need to be completely, they've been undersampled, so we need to sample them much better. But the hope is that in the next few years, we'll have light curve for this that then can be attached to the LSST1. So we have almost, in some cases, 20 years of continuous observations. And this is just an example of one of the first 4 square degrees that we got of one of these fields, and some zooming in just to show you that although this is a very preliminary reduction, you have a lot of these objects, and in here you would have to dig the millions of AGN that LSST will provide. So with this, I just leave you saying, the next step would be to join X-ray and optical and understand how X-rays may produce the optical variability to reverberation in the disk. This is a more complicated topic still to be addressed. But so I think I would just leave you with the conclusion, hoping to convey the message that in the next few years, the variability not for specific object, but for huge sample will become, an industry, and there is a lot of to dig in and a lot of discovery space. Thank you.
Some questions?
So, you assume that when you do the scaling with a black hole mass, you assume that all AGN or lasers are getting at the same eddy contraction?
No.
Okay. So there is an eddy contraction factor there?
Yes and no. In the sense, there is 1 degree of freedom there that could account. With our data, you could not properly probe the eddy contraction. So there is space for changing one of the parameters, the B parameter in front, in which you can change the eddy contraction. If you take the average value of the sample, you get an accretion of 10%, which is the average that we believe AGN accreted. So it's compatible with the average. There is not explicitly a factor for each individual AGN, because then that would reflect on the luminosity, and the luminosity is changing with time. So you need to use the average luminosity for each object. So there is space for a dependence, but from our data, we cannot say clearly that there is.
Because I was wondering whether there is any dependence on the variability on the eddy contraction.
Yeah, the model expects this. In the previous model, the idea was that the break moves, but also the normalization way would anti-correlate with the accretion. Okay. So, but with this sample, we cannot strongly constrain if that's the case.
Yes.
Because you talked about differences between type 1 and type 2.
Yeah.
Is that strongly study taking into account that you may have changing
Not in what we did, in the sense that changing look are a fraction, and changing look obviously will behave differently. But this is one of the things that you could possibly do. For instance, changing look would be the most extreme cases of variability. If you have an object that varies very little according to the structure function, and then at some point its light curve starts changing a lot more, then that's candidate changing look AGN. Right? And then maybe you can follow it up and look for it. In the work that we've done, we didn't have the spectra to see if each one of these is a changing look. Of course, some of the sample, like I think one Vincenzo was looking, are partially clean. For instance, you remove objects with strong outflow, with broad absorption line to try to make a sample of relatively average clean quasar and AGN. But there is a lot of space. And of course, for LSST, that's one of the targets. So they want to target changing look AGN, discover how many there are, how frequent it is, and use it to map the environment around the black hole and the outflows. Yes, that's a huge discovery space. But then we need correlation of variability and then follow-up spectroscopy to that problem.
Yes.
So I'm wondering why are you so surprised about the lack of variability of supertools? I mean, under the standard paradigm, that in supertools we don't see directly the broad dimension, so we don't see directly the emission risk, or the emission is the process. So why is such a surprise?
Because it depends. If the radiation is reprocessed, is absorbed emitted on larger scale, then you dilute the variability. But if you just absorb it, it just should go down, but you cannot change the time scales. So you should just have that variability goes down.
But we know that we not observe because the optical colors of supertools are not much redder than the optical colors of supertools.
Yes, so and in fact, probably that's the explanation, although it has to be properly modeled. See if we can, with you know, the reflection and torus, properly model that behavior. So that's something that that has been properly done. There are models trying to do that, especially in the infrared with the torus, you know how much. But we just realized that there aren't many studies in detail of variability of type 2s. So I'm not completely surprised. So it's one of the two possible outcomes that I expected, but it's not necessarily one, or probably it's a combination of the two. You know, part is absorbed, some is reprocessed, and then you have to come out with what you observe.
Another thing that you were surprised of the flattening of the structure function. Wouldn't you expect the structure function to flatten sooner or later? I mean, probably when you reach a size that is, I mean, there are no AGN larger than that.
Yes, yes, absolutely.
So,
but in the point, yes, I'm surprised because, for instance, in Vincenzo's sample of quasars, you don't see that. It keeps going up. And we didn't expect, well, there are claims that the typical time scale on which the variability should flatten was around 3 years, based on that random walk. But then when we were looking, there are other studies that say, no, we don't really see that. And in Vincenzo's case, if we had this one that I showed you before, this one, in this case, it doesn't, you know, it keeps going up. So in this case, it doesn't flatten out to 10 years. And in the other case, instead it does. So
this is what is the time scale of this 10 to the minus 3?
So this is in days, this is 1,000
days of 3 years.
Yes.
And
so it could flatten out right here. Yes, of course. Okay. The other one, but this is the rest frequency, right? Vincenzo. This one, let me see, it was, this goes, I think, to more or less, we're going rest frame. Here it's 3. Okay, so
this is days. Long days.
Yeah. Okay. So this is sorry. This is 3. It's the same. So if you assume, you say, okay, but it could be like this. Yes. Now we have only 1 point so far here. So now we keep. So you have to see what happens later and see if it's consistent or not. Because at face value, when we derive that, this plot is much. So it's in agreement with some studies and not with others. Now, it could also be that the mass is in there and the sample are different samples. So it depends on the time scale. So you need a very large sample because you need to cover all type of masses and time scale and wavelength properly doing some stuff. Plus, when you change redshift, you change wavelength, and Vincenzo and others show that the variability depends on wavelength. So to put everything in a correct scenario, you need to very large sample to have very good light curve well sample in different bands, covering a large range of directions.
Maybe in this sample there are agents with lower mass.
Yes.
So they are just smaller.
Yes, and there will be because the others are quasars. Well, this is a slightly more general sample, but not order of magnitude difference, right?
Okay, if there are any more questions? I don't see any lines, so thanks.